Okay.
I didn't take mine before. I thought we were good.
All right, let's get started. We are in lecture 21. That means we're, like halfway done with the semester. Can you believe that? We are halfway done. It's kind of nuts. I checked on Blackboard this morning, and homework 5.3 and 5.4, I think they're being graded right now, but I have the solution posted. This solution became active like this morning. Homework 5.5 was due today. How did the concentrated moment homework go? Hopefully it was pretty easy. Like, I don't think that one was intended to be very challenging, and the cantilever beam should have been really easy. So, okay. Today we're going to discuss shear and moment diagrams for beams with internal hinges. That's really the star of the show today. We kind of already talked about internal indeterminacy in beams and frames. We talked about that last time. And it's really just a footnote. I just wanted to close the loop on that. But what I want to talk about, what I really want to focus on is shear and moment diagrams for beams with hinges. So let me open those notes back up. Because that's going to take us a little bit of time today to get through that problem. Okay, so just make sure we're on the same page. So we're using the same relationship. Nothing's changed from our fundamental theory. So we have our relationship between load and shear and moment. And the long story short is what we're doing is we're integrating the load diagram to get the shear diagram and integrating the shear diagram to get the moment diagram. Now we're not breaking out the dx's and the curly little s's because for the most part we can use our graphical relationship between lines and parabolas and things like that to basically construct the shear and moment diagrams graphically. And so what we can do is recognize the relationship between load and shear, that at any given point the slope of the shear diagram is equal to the load, and between 2 points the change in shear is equal to the magnitude of load. And we can use the same relationship between shear and moment to construct those shear and moment diagrams graphically. And for the most part, we're able to do that really without any calculus at all. There was only one problem that we had where calculus helped, and it was just sort of a check just to make sure that what we were doing was correct. We didn't actually need to break out any derivatives and integrals to actually do the problem. It was just a nice little check. Let's see. Oh, wait, is this the wrong one? Oh, yeah, that's the wrong one. I opened the wrong presentation. Lecture 20, and I opened up lecture 20. I was like, something's not right. We've already talked about this. Okay. All right. Last time we talked a little bit about stability and determinacy, and I'm not going to go through this in great detail again. Just recognize that in our last exam, we were able to classify structures based on their external stability and determinacy. We were also able to classify trusses on their internal stability and indeterminacy. We hadn't yet talked about beams and frames and their internal indeterminacy. And so the expression is very similar. And really all we're doing is we're collecting all of our unknown quantities for beams and frames on one side and our known quantities on the other. So our unknowns are the support reactions, and then for every member we have 3 unknowns because we have axial, shear, and moment. And then for our knowns, we have any releases, any hinges, and then for every joint there's 3 equations of equilibrium. And so we're able to write an expression for internal indeterminacy pretty easily. And the nice thing about the expression is that there's a special case. So this expression is by default for frame structures, but a beam is just a frame with 1 member and 2 joints. So if you take beams and then set m equal to 1 and j equal to 2 and plug and chug, you actually get the same expression as IE. So I mentioned that really for your benefit on the FE exam, because when you open the FE reference manual, the only 2 expressions that you're going to have are this one and this one, but this one resolves to the external indeterminacy one pretty easily. So I just throw that out there in case you're wondering, where did it go? Well, it's baked into that. Okay, so really the star of the show today is shear and moment diagrams for beams with internal hinges. And we haven't yet discussed how internal hinges affect the construction of a shear and moment diagram. And the short answer is they don't, okay? The longer answer, the more elaborate explanation of that is that when we construct a shear and moment diagram, we're using reactions. And so whenever we have a beam with internal hinges, we use the fact that the sum of the moments are 0 at that hinge. We use that equation in order to solve for those reactions. So those reactions already satisfy that internal equation of condition. They already meet those requirements. So once you solve for the reactions, you can kind of ignore that hinge, and you'll find that when you construct the shear diagram and you construct the moment diagram, that the result matches probably what you would expect, okay? And so I really want to spend most of our time today discussing this problem because this is going to get our gears turning, as it were, in performing this analysis. Now, I have not given you the support reactions on this problem because that's kind of part of the challenge with this. I want to go through and do this problem start to finish. So I'm giving you a sort of a propped cantilevered beam. So I have a fixed support here at A, and I have a distributed load and a concentrated load in that left span. I got a hinge right here, and then a roller support at B, and I want to be able to draw the shear and moment diagram for this structure, okay? And so remember, anytime I have this little white circle there in the beam, that's emblematic of a hinge. So let me pull up my notebook here, and this one, I don't want to say this one's going to take a while, but I really want to take our time with this one. So we're going to go through this one sort of start to finish. I'll give you all a sec to jot this down, and then we'll get right to it. Everybody good for me to go ahead and start, or you need a minute? Okay, I'm seeing some nods, so we can go ahead and move on. Okay, so I want to be clear that this problem isn't any different than any of the problems we've done before. I mean, we're still going to use the same approach, but with this internal hinge, we're going to have a little bit of extra work to do. Now, to begin, first thing I want to do is I want to start by identifying my unknown support reactions. So how many unknowns am I going to have at support B? 1. And how many unknowns am I going to have at support A? 3. All right, okay. So we have a vertical reaction here. We'll call it A. And for the sake of discussion, I'm just going to assume that all of my vertical reactions are acting upwards. So we'll call that BY. We'll call this AY. I'm going to have a horizontal reaction here. We're going to call it AX. But what is that horizontal reaction going to be? 0, right? Because if I sum forces in the x direction, oh, they decided to get away from me there. So this is just going to tell us that AX equals 0. So this one's sort of a freebie. Okay, so we'll just put, let me do this, and we'll say AX is 0. We'll just do that. And then we're going to have so there's 3 reactions here, vertical, horizontal. We're going to have a moment reaction here as well. So which way do you want me to assume, clockwise or counterclockwise? You tell me. Counterclockwise. Okay, counterclockwise. So we'll do counterclockwise. And remember, if we get a negative answer, it just means that our assumption was incorrect. Doesn't mean that we did anything wrong, just means the reaction's going the other way. Okay? Now, let's see if we can look into the crystal ball a little bit and see what's going to happen here. Okay, so let's see. If I employ my sum of forces in the x direction equation, that's going to give me the horizontal reaction. So let's ignore that one for right now. Okay, so I have 2 more equations of equilibrium for the structure as a whole. Okay, so let's see what happens if I sum forces in the y direction. What's going to happen if I sum forces in the y direction? How much force do I have going down? Well, I've got 90 kips, and I've got, what is that, 3 kips per foot times, what is that, 80? So 240. So 240 and 90, what is that, 330? So I have 330 kips going downward. What do I have going upward? AY and BY, right? So if I employ the sum of forces in the y direction, like let's go ahead and do it. Let's just sort of see what happens. So if I sum forces in the y direction, so So if I sum forces in the y direction, what do I got? I got AY, BY, and I have 90 kips, and I have 3 kips per foot times 50 plus 10 plus 20, or 80 feet, right? So AY plus BY is 330, right? So what's AY or what's BY? Am I able to solve for either one of them right now? No, right? Looking at the structure as a whole is not going to tell me what AY or BY is. All it's going to tell me is a condition that these two values must satisfy. So what I'll do is I'll put a nice little box around that, and I'll call that equation 1, okay? What about if I sum moments? What about if I sum moments? I could sum moments at A if you would like, for the whole structure, but that one's not going to help me out either, okay? Let's see what happens, okay? Let's see if we can work through this. So if I sum moments at A, do I have to consider AX or AY? No. But I do have to consider MA. That is a moment, right? So MA is going to be a moment right here, right? What about the 90 kips? Does the 90 kips generate a moment at A? Yeah, so it belongs on this side of the table, and what's my moment arm? 90 times 50, there you go, 90 times 50. So this is 90 times 50. All right, what about the distributed load? Does the distributed load generate moment? You bet. So it's 3 kips per foot. Let me see if I can, we'll move this over a little bit. I must say I get kind of spoiled with that because you can't do that on a whiteboard. All right, so 3 kips per foot over a distance of 80 feet. Is that all, or do I need something else? Am I missing something here? Say it again? Yeah, so, well, 3 kips per foot over 80 feet will give me the load, but I then also need the moment arm. That's 100% right. Does that make sense? Because what I would do is I would collapse that into a single point load, and the single point load would be 240. It'd be 80 times 3. Make sense? Okay? But what's left? What am I missing? If I'm summing moments at A, what did I forget? BY. And so BY generates moment at a moment arm of 80 feet, right? So BY times 80 feet. All right? So y'all help me out. So on this side, I've got MA plus BY times 80 feet. And on this side, I've got 90 times 50. What is that, 4,500? What is that, 240 times 40? Was that 9,600? Did I do that right? 9,600? I'll move that over just a little bit more. Just to make sure. So what is that? What's 4,500 plus 9,600? 14,1? 14,1, did I do that right? 14,100? Can I get a second on that?
Yep.
Okay, all right. Same problem though, right? I don't have an answer, okay? I know that comparing AY and BY, if I sum them, I should get this. And I know that comparing MA to BY, if I sum these in this fashion, I should get that, but it's not telling me the answer. I don't have a number, okay? So let me move that over a little bit. And so now I've got 2 equations, but I'm not any closer to the answer, okay? So what do? Whenever you see an internal hinge, that should spark something. There's something we ought to try. What should we try? We should cut a section. We should break out our secret weapon of structural engineering, the samurai sword or the lightsaber if you're a sci-fi fan. So we're going to cut a section through the hinge, okay? So I'm going to cut a section. We'll call it section 1-1, okay? And you tell me, would you like to cut a section and look to the left or look to the right? Right. There's less stuff going on the right, and I don't want to have to draw too much, so let's cut a section and look to the right. So I'm going to scroll down a little bit. Okay, so let's just make sure I get everything. So cutting to the right, I've got a distributed load, 20-foot beam, and the reaction at B. Okay, so let's draw ourselves a little line right there, and we'll say section 1, 1. We'll say looking right. All right, so let's make sure we account for everything. Okay, so what we've got. So here's our beam. And there's where we cut our section. We've got our distributed load. What was the magnitude of that load again? 3 kips per foot. We've got our roller. Okay. We have our reaction here. And then this distance, what was that distance again? 20 feet. Okay. Now, whenever we cut a section through an arbitrary point in a structure, we have at most 3 unknown components. Do we have 3 unknown components at this point? No. Why? Because the moment is 0. It's a hinge, right? There is no moment at the hinge. So really all we have going on is we have the unknown shear. So there is a shear at this point, right? We agree on that, right? We're going to solve for that shear, just for the heck of it, okay? Now, if we draw a positive shear, remember when we cut a section and we look to the right, positive shears are upwards. So we have an unknown shear, so we'll call this shear at the hinge. And I guess we also do have an axial force at the hinge, but what is the axial force? We'll call this P hinge. What is the axial force at the hinge? Well, are there any horizontal forces going on at all? So what's the axial force? 0. There is no axial force. But we are going to solve for this vertical, or this shear at the hinge. Just so you're aware, we're not going to directly use that value at all, but there's a reason I'm solving for it, and you'll see. Okay? Now, I'm going to take this distributed load. I don't like dealing with those if I can avoid it, so I'm going to collapse that into a single point load. How much is that point load? 60 kips. And how far away from my section? 10 feet. Okay. So now what I will do is I will sum moments. So what we'll do is we'll say sum moments at the hinge, and I'll put like a little arrow right there to say I'm summing moments at the hinge looking right. So that equals 0. Okay. So summing moments at the hinge, setting that equal to 0. So what do I have? Do I have to consider these at all? Okay. So I've got 60 times 10 and by times 20, right? So okay, so 60 times 10, I can do that one in my head. That's 600. Is by times 20. And so what's by?
30.
Why did I draw 2? All right, and just for laughs, if I sum forces in the y direction, okay, I'm going to have 60 kips going down, and I'm going to have V hinge going up, and I'm going to have by, but that's also 30 kips going up. So would you agree that the shear at the hinge is 30? Would you agree with that? Let me I want to have that as a reference. Okay, so we'll say at the hinge. So shear is, and we got a positive 30. And just to make sure everybody's paying attention, what's the moment?
0.
0. Let's just see what happens. Okay. Now, let's make sure everybody's with me. So, tell me now, what do I do? What do I do?
Substitute your equations.
Exactly right. You're both saying the same thing. Exactly right. So I have a by value. Now I need to sub that into here and here to determine my remaining reactions. So what we'll do is let me scroll this down a little bit. Ooh, not that much. There we go. So what we'll do is we'll say back to equation. We'll call this equation 1. And so that was AY plus BY is 330 kips. Well, I now have a value for BY. Here's my value for BY right here. So what we'll do is we'll say AY plus 30 is 330. So therefore, AY is positive 300. So there's this reaction. And then back to equation 2. So we have 14 100 foot kips is MA plus BY times 80, right? I'm just getting that from the top of the screen. So 14 100 is MA plus BY. Now I know what BY is, that's 30. So what's MA?
1,700.
11700. Do I have a second on that?
Yes.
Okay. Foot kip, so 11,700 foot kip. Which way did we assume MA was acting? Counterclockwise? So that means that is correct. We've got the correct assumption there. All right. Okay. Now, is everybody with me so far? Okay. So, I want to be clear that, okay, here's my reaction for B, here's my vertical reaction for A, here's my moment reaction for A. Would we have been able to solve for those reactions had we not done this analysis and assumed that moments at the hinge were 0? Would have been impossible, right? We tried to ignore the fact that we had a hinge. We came up with this, right? We weren't able to solve for a reaction. It was only when we recognized that the internal moments at the hinge were 0 that we were able to get values for our reactions. I posit to you that these reactions satisfy the requirements at the hinge. So from here on out, we can kind of ignore the hinge, okay? And if you don't believe me, watch, you'll see what happens, okay? Now what we're going to do is we're going to draw the shear and moment diagrams, okay? So I'm going to drop down here and I'm going to redraw my structure with the reactions on there, okay? So bear with me. Okay, so Okay. Okay, so here's the beam, and we'll say the hinge. We're going to put the hinge on here. We'll put the hinge about right there. Again, we're going to put it on there, but we can kind of ignore it for the purposes of our shear moment diagram. Okay, so we had a distributed load. Across the entire beam. Okay, so that's 3 kips per foot. Okay, we have a, let's see, a load about right here, and that load was 90 kips. And then we now have reactions. We have a reaction at point B. This reaction is 30 kips. And then we have a reaction right here. This reaction is 300 kips, and that's A. Then we have a moment reaction that is counterclockwise, and it is 11,700. Okay? And there's our structure. Okay? The only thing left to do is to put dimensions on this. So this is 50 feet, 10 feet, 20 feet. 50 feet, 10 feet, 20 feet. So there's our structure. And now we have our free body diagram figured out. All of our reactions are in place. So now it's time to start drawing. So I'm going to give myself a little bit of room. Not that much room. And draw my little dashed line so that everything's kind of lined up. So, one thing I'll tell you, because this is a common question I get, and I'll go ahead and throw it out there. So on exams, I will usually have like this, the guidelines drawn, and I'll have like flat lines to where you can start the shear and moment diagram. You don't have to worry about this stuff, if that makes sense. Like there'll be space for you to draw it. So. Okay. All right. So now let's start off. Let's start off with our shear diagram. So when we construct our shear diagram, so first off we want to start at 0 and end at 0. And so now that we had a hinge and all this stuff going on, let's see if that actually happened. Okay. See how we're doing on time. Oh, we're doing fantastic on time. Okay. So, all right. So somebody help me out. What's the first thing I need to do? Tell me what to do. Go up 300. So I'm at 0. I'm going to go up 300. Okay. I go up 300. So we've got a distributed load, which is pretty much everywhere on the beam. So everywhere in the shear diagram, if we have a constant load, what does the shear diagram look like pretty much everywhere? Linear, right? So what do we have? So from 300 to here, bless you, from 300 to here, how much load is that? 150. So 300 dropping down, we should be at 150 right about here. So that's going to be about like that. So we'll call that 150. And that is going to be a linear drop, right? And just so we're all paying attention, what is the slope of that line? 3. Because it's 3 kips per foot. So what happens right here?
Goes down 90.
Goes down 90. So if I'm at 150, drop down, puts me at 60. Now I want to be clear, okay? I drew a line right here, but we can ignore that hinge. I want to be crystal clear. That hinge doesn't matter anymore. It doesn't matter. So let's ignore it for a second. So what happens from here to here? How much do I drop from here to here?
90.
So if I'm at 60 and I drop down 90, what does that put me at?
Negative 30.
Negative 30. So that's going to look something about like this. And that's going to bring me back up. Okay? Let me see if I can do a little bit of a better job with that. We'll try. That's about the best you're going to get. That's a line. I promise it's a straight line. It doesn't look like a straight line, but it is. Okay, I'm going to try it one more time. That's going to bug me foul. Okay, that's about the best you're getting out of it. I'm not doing it again. So, okay, we ignored the hinge, right? Ignored it. Now I want to go back to it. Could somebody tell me what is the shear right here?
0 or no?
No, hold on. So I'm at 60. If I'm at 60, how much do I drop from here to here? 30. So if I'm at 60, I drop down 30. What do I get? 30. Interesting. What did we get right here? We got that the shear at the hinge was 30. Well, by golly gosh gee. It's like we did something right. Pretty slick, isn't it? It's like all that static stuff makes sense. Okay. So far so good? So we have our shear diagram constructed, and remember the slope of all these lines is still 3 kips per foot, so we'll put, maybe we'll do this. 3, 3, 3. Okay, so now we need to start computing some areas. Let's start off with this part right here on the right. If this is 30 and this is negative 30, what is this distance here and here? What are these distances? 10. They're even, right? So this is just 10 feet, right? So this is 10 feet. This is 10 feet. So what's the area under the shear diagram here and here in these regions? 150, right? Because 30 times 10 over 2, right? So this one, that one's going to be minus 150, and this one's going to be plus 150. Okay? What about this one? Do y'all remember how to do the trapezoid, right? So we'll just average 60 and 30. What's the average of 60 and 30? 45, right? What's 45 times 10? 450. So this one is going to be positive 450. And I want you all to help me out. What's the area under the shear diagram in this region? So we're averaging 300 and 150 and multiplying it by 50 feet. Anybody have an answer for me? 33,750. You might want to check that again.
It's 300 and 150.
300 and 150. So we're taking the average of those. So the average should be about, what, 225?
225.
And then 225 by 50.
11,250.
11,250. I think you might have had a digit wrong.
I multiplied it by 150.
That'll do it, yeah. 11,250. Okay. Sound good? Now, up until now, we've always said that when we sum the areas under the shear diagram, they, for the most part, should be 0. Are they 0 here? No. Okay? So I'll put a note. What is the sum of the areas under the shear diagram? When you sum that out, what do you get? So these two are going to cancel. 150 and negative 150, those cancel. So So what does those add up to be? 11,250 and 450, what is that? 11,700? So, interesting. Do we see that number anywhere? That's the reaction, right? That's the reaction at A. So that's how when we construct our moment diagram, that's how we're going to get back to 0, is because we're going to have a sudden drop of 11,700 foot kips right there at A. So let's go ahead and do that. Now, sorry. Let me drop that down a little bit. Let's do that. Okay, so I'm going to draw my guidelines down a little bit further so I can kind of see what's going on. Now, for my moment diagram, is my moment diagram going to be linear? Is it going to be constant? What are the regions of the moment diagram going to look like?
Parabola.
They're going to be parabolas, right? If I have a linear shear diagram, I have a quadratic moment diagram. Remember, you're integrating, so it's one level up. So we start out at 0, and again, that sudden, that moment reaction at A, it's got to be a sudden drop, right? The sum of my areas is a positive 11,700, so to get to 0, I've got to have a sudden drop in 11,700. So that moment reaction at A, what it's going to do, I'm going to start off with that. Okay. Let's do that. That way we can kind of see what's going on. Okay. So the way I draw moment diagrams, I like to first make sure I'm getting my values right. So if I'm at negative 11,700, what am I going to be right here? From here to here, how much do I go up? 11,250. So if I'm at negative 11,700 and I go up 11,250, what's that put me at? Negative 450. Okay. So we'll say, we'll put that about like that. Okay. So we agree it's quadratic, right? So is it option 1 or option 2? 1, right? Because we have a lot of shear, so a lot of shear to less shear, so a lot of slope to less slope. So we're going like that. So if I, let me get this out of the way. So it's going to look something about like this. Okay? Something about like that. Okay? Then if I'm at 450 and I go up 450, what's my value right here? 0. So this is 0. Okay, let me draw another little guideline right here. And then I'm going to go up 150 and then back down to 0. So I'm going to do my best to try and make this a consistent parabola, but it's going to kind of look like that. Is that fair? That's about the best you're going to get out of me from an artistic standpoint. Okay. So far, so good? Now, here's something that's kind of interesting. We sort of glossed over that our moment diagram is 0 right here. Where is that?
The hinge.
That's where the hinge is. So if we scroll up, we can see that our moment diagram is 0 right at the hinge. So this is what I was getting at before when I was saying, whenever you're constructing the moment diagram, once you get your reactions, sort of just ignore that hinge is there, okay? And if done correctly, you will get the internal response that's correct, okay? It's exactly what happened here. We got a shear of 30, and a moment of 0 right at the hinge, which is exactly what we got when we did statics, when we just cut a section and used equations of equilibrium. Does that make sense? How are we feeling? It's not too bad, right? When you're constructing a shear and moment diagram for a beam with a hinge, it's usually a little bit more work because you've got to cut a section and then back substitute, do all that. So it's usually a little more involved, but I kind of like the process in the end. And again, I think with shear and moment diagrams, they offer a really beautiful way of self-checking, right? If you computed your reactions correctly, then the shear and moment diagrams will close, right? To use a surveying term. They will close. They will start and end at 0. Okay? Does that make sense? All right. So the only thing left to do, and we will do this on Wednesday, is I'll pull up the notes here just to kind of illustrate. So the only thing left to do for shear and moment diagrams is this. Okay? So we're going to draw shear and moment diagrams for frames. And so this is going to be the problem that we do, and I'm giving you the reactions. Tomorrow is going to be a really short lecture. I might begin our discussion on deflections on Wednesday just to make sure we're utilizing our time effectively. But really, the shear and moment diagrams for a frame is the same thing as the shear and moment diagrams for a beam, just instead of drawing like this, we turn the member and we're drawing like that. That's it. So if, for example, here's some elements of a frame, and so if we're trying to draw the shear and moment diagrams for this column, so we look at the column and we say we go over 18, over 18, and so there's the shear diagram, and then the moment diagram, well, the integral of this is a line, so it's a triangular moment diagram. And that's pretty much it. I mean, if anything, frames maybe will help explain. I don't think I did it on this problem. Yeah, I didn't do it on this problem, but might help explain why, for the longest time, I've been putting these little tick marks here on my my shear and moment diagrams. And really, what the tick marks are, they're arrows. Okay. So basically, what I'm showing is that I'm drawing the shear diagram from left to right. So, like for columns, I'm going to draw the shear diagram from bottom up instead of top down. Because that orientation actually does matter, because if you draw it, let's say, the opposite way, then you might get your diagrams flipped. It doesn't mean the values are wrong, but the orientation might change. So that's sort of an important aspect of when you analyze structures with software packages, but we'll get to that later. Sound good? All right, I'm going to pull up the code one more time if anybody missed it. I'm giving you 7 minutes of your life back. I will see you all on Wednesday.